For years, interacting with a language model meant receiving a single linear string of text. Today, advanced reasoning engines represent text generation as a vast, branching network of potential decisions. We are going to look at the exact mechanics required to upgrade a standard language model into a self-correcting reasoning engine, using the architecture found in OpenAI's o1. We will map out the specific implementation steps, starting with the chain of thought prompting techniques, established by Jason Wei and his colleagues, leading to the open-ended Marco o1 framework. This architecture uses a multi-step search process to find the most accurate solution for a given problem. The foundation of this system is chain of thought, or COT. This technique requires the model to generate intermediate reasoning steps before arriving at a final answer. To implement this, you must structure the model's generation into a strict triad: the input question, the chain of thought process, and the final output answer. In a math word problem, the model calculates the subtotals within the intermediate steps, adding those individual results together before outputting the final sum. There is a specific parameter threshold required for this logic to hold. Language models under 100 billion parameters often struggle with logical coherence across these steps. They frequently hallucinate intermediate facts, even if the final text appears fluent. We solve these linear limitations by introducing Monte Carlo tree search, or MCTS. This algorithm simulates multiple future sequences of actions to identify the most reliable path. When MCTS is integrated, several potential logic paths radiate from the reasoning stage, creating a complex decision tree. To build this search tree, you must treat the model's generated text as a series of discrete, measurable actions. These actions originate from specific reasoning states, or nodes, allowing the system to track exactly where a logic chain begins and ends. If the model identifies an error on one branch, it can explore alternate routes within the tree to find a correct solution. This integration enables a multi-path exploration of the entire solution space. Managing thousands of potential branches requires a mathematical reward signal to navigate the tree toward the correct result. This formula defines the reward signal by calculating a confidence score. It compares the log probability of a generated token against the top 5 alternatives, applying a softmax function to normalize them. Averaging these scores provides a definitive numerical value for the reasoning path. We also set the action granularity, the amount of text generated at one time. Here, a full reasoning step misses a nuanced calculation error. By constraining the action unit to smaller 32-token mini-steps, the model catches these errors earlier. Combining these mini-steps with the confidence scoring formula allows the model to validate its own logic at a microscopic level. To handle logic dead ends, you must build a self-correction mechanism directly into the inference pipeline. This is done by injecting a specific reflection trigger. You prompt the model with the text, "Wait, maybe I made some mistakes. I need to rethink from scratch." This prompt forces the model to act as its own critic. It reevaluates its prior outputs, abandons the failed branch, and routes its logic toward a successful node. This same architecture can be applied to ambiguous challenges that lack a single correct mathematical answer. In this translation task, the model analyzes a Chinese slang phrase. As shown in the breakdown, the model identifies that a literal translation would be crude in English. It reasons through more appropriate equivalents, eventually selecting comfortable soul to match the intended meaning. This framework enables models to navigate cultural nuance, ambiguity, and subjective human intent. The completed architecture integrates chain of thought, MCTS, confidence scoring, and reflection. These individual components combine to form a unified problem-solving engine. Future development involves replacing the confidence score rollout with outcome reward modeling and process reward modeling. These specialized systems grade both the final answer and the individual reasoning steps to reduce search randomness. Using this blueprint, you can now build and refine your own open reasoning models to push the boundaries of local inference.